Right, match each function with its graph. All right, so let's take a look at h of x. So I see there's going to be a 0 at x equals -4. So there's going to be a 0 on top, but there's no, it won't cancel out on the bottom. There's no 0 on the bottom that's at x equals -4. So -4, yep, there's a 0 here. There isn't here. There isn't here. And there isn't here. Wow, that was pretty quick. All right, so I already know that it's going to be this one right here. But let's just check the rest of the details because, you know, we're here to learn. We know that there is an asymptote at -5/2, and sure enough, -5/2, that's like -2.5. Yep, that's about -2.5. You have yourself an asymptote of order 1, so it's going to be different going, it's going to go upward at the top, or sorry, one's going to go up and one's going to go down. If it were order 2, they'd either both go up or both go downward, depending on the equation. And what else do we got? Oh yeah, the degree on top and the degree on the bottom are equal, so we know that we have a horizontal asymptote at 1 divided by 2, so 1/2. And sure enough, look at, you see that this is not approaching 0, it's actually approaching 1/2. Same with this, it crosses and it's approaching 1/2. Right, so definitely A is A. All right, let's take a look at B. So I see x minus 2 on the bottom, so I should expect, oh, but is there an x minus 2? Let me take out this 2 here. All right, I factored out the 2, and sure enough, there's an x minus 2 both on top and bottom. That's going to create a hole, but not an asymptote. So this is just basically m of x equals 2. That's just a straight line across at 2. That's this one for sure, with a hole when x equals 2. Because if you plug in x equals 2 here, then you're going to get 0 over 0. That you're not allowed to divide by 0. That's undefined. But everywhere else, let's say you put in a 4, you're just going to get 2 over 2 cancel. If you put in a 6, you're going to get 4 over 4. They cancel. So it's always just going to be mx equals 2 everywhere with a hole at x equals 2. Yeah, definitely C. So this one right here is definitely this one right here. All right, let's take a look at part C. F of x is 3 over x minus 1. All right, so we see that there are not going to be any zeros because nothing will make the top 0. So it cannot cross the x-axis. So I already know it's not that one, but you can see it's not that. It's not this one because this one crosses. This one does not cross. That seems like it's a good candidate. This one doesn't cross, but there are other things. We already know that's B. So let's see what else. So you definitely have an asymptote at x equals 1, and that's what rules this one out too. So it is definitely this one. And if you look at x is 1, sure enough, we have an asymptote right there. And what else? Oh, let's see the end behavior. Since the degree on the bottom is greater than the degree on the 1, this, when x gets really big, this is going to blow up. This one won't. So you're going to have small over large, and it's going to approach 0. And sure enough, this guy approaches 0 on both sides. Yep, definitely C, say it, is this guy. Or this girl. Who knows? All right, let's take a look at part D. G of x is 2x minus 3 over x plus 2. I might as well factor out the 2 here. All right, so we have a nicer version over here. You can see nothing cancels, so there are no holes. You have an asymptote at x is -2. Yeah, that looks right. If this is -5, this is about -2. It's of order 1, so it makes sense that it would go up on one side and down on the other. You have a 0 at x is 3/2, so 1.5. And yeah, that looks like about 1.5. That makes sense. And it looks like they're the same degree on top and bottom, which means the horizontal asymptote will be at 2 over 1, so at 2. And sure enough, this looks like it grows to about just under 2 here. It's approaching 2, and this shrinks just about 2. So yes, it does have that horizontal asymptote. Look at the y-intercept. Might as well take a look at that as well. If I put x as 0, I'm going to get -3/2 times 2. That's going to be just -3 over 2, -3/2. So yeah, -1.5. Yeah, that's about right. Okay, so it looks like this guy, whatever, is this one right here. Great. Let's go to question number 2. Consider the function f of x equals 3 over x minus 2. All right, I considered it. Great. Part A, state the equation of the vertical asymptote. So there's a vertical asymptote when x equals 2. Yep, that's the equation. It's got an equal sign. That's an equation. Use a table of values to determine the behavior or behaviors of the function near its vertical asymptote. Oh, that's a junky way to do it, but I guess we have to now. All right, so I took numbers just to the left and just to the right of 2, and I did 2 for fun. Of course, if I plug in a 2, you get 3 divided by 0, that's undefined. If I plug in 1.999, which is just to the left, I get 3 divided by 1.999 minus 2, which is 3 divided by negative 0.001, and that's going to be negative 3,000. And if I plug in 2.001, which is just on the other side of the asymptote, so 3 divided by 2.001 minus 2 is 3 divided by positive 0.001, and that's equal to 3,000. So as you can see on the, if I were to do a little graph, you could tell that just to the left it goes way down, and just to the right it goes way up. Right, just to the left you're at negative 3,000, and just to the right you're at positive 3,000. Right, part C, state the equation of the horizontal asymptote. Well, the degree on the bottom is larger than the degree on top, so obviously when x gets really, really large, this is going to get really, really big. The small will stay small, so small over big is it always approaches 0. So the horizontal asymptote is at y equals 0. And I could draw that. It just kind of goes like this and like that. All right. Use a table of values to determine the end behaviors of the function near its horizontal asymptote. All right, so we'll just plug in two, like a really big number positive, a really big number negative. That should do it. All right, so plug in 1,000. You get 3 divided by 998, and you get 0.003006012024025. And you plug in negative 1,000. And it's basically 3 divided by negative 1,002, so you're going to get negative 0.002994011976005. So this one's like very, very small but negative. This one's very, very small but positive. But honestly, we could have done so much better than the table of values. We could just have looked at this and said, we know the top is positive. If I plug in a really big number, the bottom's going to be positive, so it'll be positive. If I plug in a really big negative number, the bottom's going to be negative. Positive over negative is going to be negative. So we knew already the signs of these guys. Table of values is really a waste of time in this scenario because we're just way too good at graphing polynomials and rationals. Now part E, determine the domain and the range. So the domain is anything that, any x that you could plug in. And so I could plug in any, I'll get a value for any x all the way across until you get to 2. You can't plug in a 2 because that's no good. You can't divide by 0. But then you can plug in any other number, no problem. So x is all the set of all real numbers, just not 2. So x just cannot be 2. The range, now the range is a little bit different. The range is all the numbers that you could possibly get as an answer. And if you look here, we're going to get all the answers all the way up to infinity, all the way down almost to 0, but you don't actually get a 0 answer from any answer, right? Because there's no way to make 3 equal to 0, right? So the top will never be 0, which means f of x will never be 0. That's the one thing you can't get. You'll get as close to 0 as you want by making the bottom really big, but you never get 0. And as you can see, you do go all the way to negative infinity as an answer. And so the range is simply all real numbers, just not y equals 0. All right, part F, determine the positive and negative intervals. All right, so looks like all this is below the x-axis. So this is a negative interval, and all of this is above the x-axis. So this is the positive interval. Now definitely don't confuse it with decreasing, increasing. So this is decreasing, but that has nothing to do with whether it's positive or negative. Positive or negative means how high it is. The value is negative. Here it's decreasing as well, but the value is positive because it's above the x-axis, right? So the value is your f of x, your y value, and it's going to be positive in all of this area and negative in all of this area. All right, part G, sketch the graph. Whoops, I've already done that, so it looks like we're done. Question number 3. Repeat question 2 for the rational function f of x is 4x minus 3. Okay, we'll just switch it up. Oh, over x plus 1. We'll just switch it up as we go along. So state the equation of the vertical asymptote. So there's a vertical asymptote at x equals negative 1. I'm just going to factor this because sometimes when you don't factor it, you miss some holes when you didn't know they were holes. There won't be here, but I'm just going to factor this. All right, this should be nicer to look at because the 0 is more obvious, x minus 3/4. So we have a 0 at 3/4. And the leading coefficient 4 over 1 is just a little bit more obvious. So it's just a nicer way to have it. You always want each bracket to have x plus something or x minus something, and then the leading coefficients by themselves out here. All right, so state the vertical asymptote, and we have an asymptote at x equals negative 1. I forgot to write that. Here it is. All right, part B, use a table of values to determine the behaviors of the function near the vertical asymptote. Like I said, this is completely useless because we know where the asymptote is, and our graph would have just shown whether it goes up or down. But anyways, they're asking us to do it. So negative 1 is at the asymptote. Let's go negative 1.001 and negative 0.999, both just to the left and just to the right of negative 1. All right, plug in negative 1.001 into here, and you get 7,004, really big number. Plug in negative 0.999, and you get negative 6,996, really big negative number. So you can see that just to the left of negative 1 is going to go really, really big, and just to the right of negative 1 is going to be really, really big negative, and so your graph's going to kind of look like that. Part C, state the equation of the horizontal asymptote. So now the degree is the same on top of the bottom, and so it's a good thing I pulled out the 4 because it's really easy to see that the horizontal asymptote is 4 divided by 1. When the degree is the same, you just divide the leading coefficients, 4 divided by 1. So the horizontal asymptote is at y equals 4. Use a table of values to determine the end behaviors of the function near its horizontal asymptote. This one I actually don't mind doing a table of values for because it's not the easiest to really think through. When you do have a horizontal asymptote, like when it's not leading towards 0, it's not as easy necessarily to see if it's going to go towards 4 from the bottom or from the top. So let's just plug in a really big number here and a really big negative number here, and let's see what we get. All right, so when I plug in 1,000 into f of x, so f of 1,000, so that's basically I'm plugging in a number way to the right. I get 3.99306, 993,006, 993,006. So that's repeated. So really, it's basically just below 4, and we already know there's a horizontal asymptote at y equals 4, and so we know that it's approaching it from underneath. Let's check out negative 1,000, and when I plug that in, I get a value of 4.007007007, and that repeats. And as you can see, it's just a little bit above your horizontal asymptote, so it comes in from the top when you plug in a negative number. All right, part E, determine the domain and range. Okay, so domain, you're just saying what x values can you plug in. So I can plug in anything except for x is negative 1 because you can't divide by 0. And on the graph, you can just see it goes everywhere from negative infinity. Oh, all of a sudden it skips at negative 1. You can't do that. And then it goes all the way to positive infinity. So just the domain is everything except for x equals negative 1. And for the range is just all the answers you could possibly get for f of x after plugging in all the x values. And so it looks like when you plug in negative infinity, you got close to 4, but then it goes all the way up to infinity, and then all the way down to, well, from negative infinity all the way back up to 4. The only thing it doesn't hit is 4 itself. It's everything above 4 and everything below 4, but just not 4 itself. So the range is all y belong to R such that y cannot be 4. Okay, now we're going to determine the positive and negative intervals. Well, it's all positive all the way up to here. This is all above the x-axis. Now it's negative all the way. Oh, there's right where it crosses here. Now it's going to start being positive again. So there's one spot where it's neither positive or negative, nor negative. And there's one little spot where it's negative, and then you've got a huge area of positive. So everything between 0 and 4 is positive, and all of this is positive. So there are going to be two intervals that are positive and one interval that's negative. And then there's, well, negative 1 is neither because there is no point on negative 1. And then there's this one spot where it's neither. So it looks like we're going to have to find our x-intercept. Well, that's easy when x is 3/4. So we have a negative interval only between -1 and 3/4, not including -1 because there's no such point, and not including 3/4 because it's not negative there, it's 0. And we have a positive interval from -infinity all the way to -1, not including -1 because there's no point, but also from 3/4 to infinity, again, not including 3/4. And part G, sketch the graph. Well, would you look at that? I already did. Question number 4. Okay, state the equation of the vertical asymptote of each function, then choose a strategy to determine how the graph of the function approaches its vertical asymptote. Oh, well, that's awesome. I get to choose. You know me, I'm just going to graph the thing and see what happens. All right, so part A. All right, vertical asymptote is at x equals -3. And there are just so many ways to figure out how this approaches. I know that there are no zeros whatsoever. I also know that if I plug in a really large number, the bottom's going to be positive, and so will the top. And this is 1 degree greater, so I know it's going to approach 0 from the top. So I could do that right now. I know it's going to go like this. Well, if there are no zeros, then I know it's not going through the x-axis, and it's got to go from here. Also, I could have just looked at the y-intercept, just plug in x is 0, and I would have known that it was 2/3. So I knew that it had to be positive here. And since there are no zeros to go through, it's definitely going to approach the asymptote from there. This x plus 3 right here is order 1. So I know that it's going to come from the bottom on the other side. They're not both going to be at the top. That's what would happen if it was order 2 or 4 or 6, like an even number. So I already know it's going to do that. It's going to approach 0 from the bottom. Well, because of course it's going to approach from the bottom. There's no zeros on this side. There's no way for it to cross this line because there are no zeros. There you go. So it's definitely going to approach -infinity from the left and +infinity from the right. All right, part B, we have a vertical asymptote at x is 5. So there it is. And we know there's a 0 at x is 1. Might as well mark that down right now. All right, let me see. So many ways of doing this. Let's plug in at x is 0. Now you got -1 over -5, so 1/5, which is positive. So I already know that this has to go through here. So since it's got to go through here and it's got to go through here, well, and there are no more x-intercepts for it to go back up, it obviously goes down to the bottom here. And x minus 5 is order 1, so it comes from up here. I know that the horizontal asymptote is at 1 because we have degree 1 over degree 1, and their leading coefficients you can see is 1 over 1. And so this just goes like this and like that. But gosh, there are other ways to know. Like the fact that the horizontal asymptote is at 1 means that it's already above the x-axis. The only time it's going to come, so over here it's got to be above the x-axis. The only time it's going to come down is here, so it's got to be below. That's another way to do it. From the right, we would have known it's above. So it's obviously not going below because it would have to cross the x-axis, but there's only one spot it crosses, and that's at 1. So it would have to go up here. So there's just so many different ways of doing it just by the things that we know about rational functions. All right, for here, our vertical asymptote for question C is at 1/2. For your convenience, I pulled out a 2 from both of these. So 2x plus 1/2 to x minus 1/2. The 2's even canceled. That doesn't really matter too much. You could keep them there if you want. You can see there's a 0 at negative 1/2. I put that on there. The y-intercept, you can see if you just plug in a 0, so x plus 1/2, 0 plus 1/2, 0 minus 1/2, you get 1/2 over negative 1/2. That's just negative 1. Well, I think it's pretty obvious what's happening. So since we know we're going through here, we know that we have to go down to the asymptote there. There's no way we come up because there's no 0 in this area. So that would be impossible. So it's going to approach your 1 there. And since it's only order 1 on the bottom, it's not going to come from down here. It's going to come from up here, and it's going to approach like that. So it was quite obvious, especially with these 2 points here, that this graph was going to go down towards negative infinity on the left-hand side and positive infinity on the right-hand side of the asymptote. Let's try part D. All right, I took the liberty of plugging in the things that are really obvious. Like I plugged in a 0 to get 9 over 1, 9. So I know that the y-intercept is 9. I plugged in I found out what the 0 on top would be. Negative 3 will give me 0 on top. So that's my x-intercept. The bottom, if I put in negative 1/4, that's what's going to give me a 0 on the bottom. So that's my vertical asymptote. And if I put in a really, really big number or a really, really small number, so like positive or negative infinity, I'm going to get 3/4. So the leading coefficients took care of that. And so I've got my horizontal asymptote. These are the same degree, so it's a horizontal asymptote at 3 over 4. All right, so now that I've got all that, I think it's pretty obvious. I know that I have to be near this asymptote on the left somehow, and which is above 0, but I have to go through the x axis here because it's only order 1, so I can't bounce off, and there's no way to go back through, so obviously I'm approaching my asymptote from the bottom. And since it's order 1, then I have to come from the top, which, I mean, knowing that my y-intercept was there anyway, I knew that I had to come from the top. And there we go. There's my graph. But to answer the question, for this vertical asymptote, it's going towards negative infinity on the left and positive infinity on the right. Let's go to question number 5. Number 5, for each function, determine the domain, intercepts, asymptotes, and positive, negative intervals. You use these characteristics to sketch the graph of the function, then describe where the function is increasing or decreasing. So that's a lot of stuff to do. All right, let's start. Part A. Domain. That's just anything you could plug in for x. So x is -5. You're not allowed to plug in. Everything else, you're good to go. Let's do all of them. Part B, you're allowed to plug anything in except for 5/2. Part C, you're allowed to plug anything in except for 1/4. And part D, you can plug anything in except for -2. You're just not allowed to divide by 0. That's all. All right, intercepts. We got our y-intercept and x-intercept. Let's start with the x-intercepts. So that's when the top equals 0. This will never happen for A, so none. Part B, never. 10 is never 0. Part C, when x is -5, and part D, okay, it looks like they're trying to trick us here. You would want to say at x is -2, you're going to have a 0, but that's not true because these guys cancel out. It's not an asymptote and a 0. This is just a hole. And so at x is -2, it doesn't exist. And there's no place on the top that's going to ever be 0. All right, let's do the y-intercepts now. That's easy. That's just f of 0 for all of them. So just plug in 0. So 3 over, here it'll be 3 over 5, 3/5. Y-intercept will be 10 over -5, -2. The y-intercept will be 5 over -1, so -5. And the y-intercept will be 2 over 10, so 1/5. Asymptotes. All right, let's start with the vertical asymptotes. Asymptote at x equals -5. Asymptote at x equals 5/2. There's an asymptote at 1/4. And there is no asymptote here. That would be a hole. Now let's go to y-intercept, or horizontal asymptotes. Here the degree is bigger on the bottom, so it has a horizontal asymptote at y equals 0. Same thing here, y equals 0. Here they're both the same degree, so it's going to be y equals 1/4. and here they're the same degree, but there is no asymptote here actually because it's just a straight line at 1/5. This one's a bit tricky. This is actually just f of x equals 1/5 with a hole at x plus 2. All right, positive and negative intervals. Let's start here. Well, anytime the top's always positive, so when the bottom's positive, the whole thing's going to be positive. When the bottom's negative, the whole thing will be negative. So whenever x is negative, really big, so negative infinity all the way to -5, this is going to be negative, and so we're going to have a negative interval. Whenever it's greater than -5, sorry, this is going to be positive, and so you're going to have a positive interval. Right about here, we've got, this is always going to be positive, so let's just check. So at 5/2 or 2.5 is where it's going to change. So when you put in a really large negative number, you're going to get a negative on the bottom, so negative interval. And anything on the other side of 5/2 or 2.5, you're going to get a positive number down here. So anything less than 5/2, you're going to get a negative interval. Anything more than 5/2, you're going to get a positive interval. Over here, let's see. All right, so we have a spot, the 0 at -5. That's where things could possibly go from negative to positive. Also at 1/4, we have an asymptote. That's another place where things could change from positive to negative. So let's just look. When you have a really, really large negative number, so anything up to -5, you're going to have a negative over a negative, so it's going to be positive interval. Between these two numbers, let's say like 0, you're going to get a positive over a negative, so you're going to get a negative interval. And on the right hand side, let's say like at 100, you're going to get a positive over positive, so a positive interval. So it's going to go from positive to negative to positive. And there's no spots in between here that could possibly change from positive to negative besides that. So if it's negative in here, it's going to be negative the whole time. Because the only way you could go on a graph from negative to positive is through an x-intercept or flip during on an asymptote. Those are the only things, right? So it goes positive, negative, positive. All right, for part D, there are no zeros. There's like no x-intercept. There are no asymptotes, like vertical asymptotes. And so there's no way for the graph to go from positive to negative because it can't cross the x-axis and it doesn't have a vertical asymptote to flip from positive infinity to negative infinity or vice versa. This is just at 1/5 all the time, so it's always positive. No matter what x value I put into this, f of x is always going to equal 1/5. For example, if I make x 100, there's 102, there's 102, they cross out, and you get 1/5. All right, so positive interval is just all of x belongs to R. Oops, that's a bit of a mistake because there is one spot where x is not positive because it doesn't exist at all. That's when x is -2. And for part D, there are no negative intervals. All right, now I'm going to sketch these guys. So I took the liberty of putting in my intercepts. All those purple dots are my intercepts. And the asymptotes I drew with purple dotted lines. There are none here. There you've got 2, and then you've got 2, the vertical and the horizontal. And now let's just fill stuff in. So I know it goes through 3/5. I know it goes to this asymptote. I know it doesn't cross the x-axis, so it must do this. And it must flip here because it's not a double. It's not a order 2 on the bottom. All right, over here, same thing. There we go. Over here, same deal. It's pretty obvious where this thing goes. It flips over to here because it's not of order 2 at x is 1/4. And over here, we've talked about it. We just have a straight line right at 1/5, excluding this one spot right at -2. There's an open hole there. All right, last thing to do is to describe when they're increasing or decreasing. Okay, so let's look at this. This guy is decreasing. You just have to go left to right and see if it's going up or down. So look, it starts at 0 and it goes down. And then over here, it starts at infinity, goes down. There's no time where it's actually increasing. It does flip from negative infinity to positive infinity, but there's no spot where that happens, right? It kind of just at -5 it doesn't exist at all, then all of a sudden it exists. So the entire time it's decreasing, except at -5 itself where it doesn't exist. Right, so over here again, you're starting at just under 0 and you're decreasing the whole time. At 5/2, it's neither decreasing nor increasing, but then on the other side, it's decreasing. So it's decreasing everywhere except at 5/2. Over here, decreasing all the way to 1/4. At 1/4, it does neither, and then it's decreasing all the way to infinity. And last but not least, it is neither decreasing nor increasing anywhere. All right, let's do question number 6 now. All right, read each set of conditions, state the equation of a rational function of this form, ax plus b over cx plus d, that meets these conditions, and sketch the graph. All right, for a, we need a vertical asymptote at x equals -2. All right, so 1x plus 2 on the bottom should get that done. A horizontal asymptote at y equals 0. So the degree on top has to be less than the degree on the bottom. So that tells me this has to be 0x plus something or minus something. Negative when x is less than -2. So when I put in a really big negative number in there, it has to be negative. So if I put a negative number in here, this is a big negative number. This is going to be negative, and so I need the top to be positive. So I definitely need this to be plus something. And positive when x is greater than -2, yeah, that'll work out. If I put a number greater than -2, this will be positive, and so the top definitely has to be positive, and it has to be always decreasing. Yeah, that'll just happen on its own. All right, so this 0x plus 1 is just 1. So this is actually just 1 over x plus 2, which gives me an asymptote at x is -2, and a horizontal asymptote at y is equal to 0. So this graph is just going to look like this. It's negative on the left-hand side. Oops. Then it switches sides and goes this way. If you plug in x is 0, you'll see that this is at 1/2 that it crosses. Now it isn't decreasing everywhere. I mean, it doesn't decrease at -2. So I think this question is just wrong. I mean, you can't have a vertical asymptote and then have it always decreasing. I think maybe they just meant never increasing, but I think they just forgot about the fact that at -2 it can't be increasing or decreasing. Everywhere else it's decreasing. So if you go from left to right, it's going down, and then even here down, so it's decreasing everywhere else. All right, let's try part B. Vertical asymptote at x equals -2. All right, so far so good. We got the 1x plus 2 at the bottom. It's the same as part A. Horizontal asymptote at y equals 1. Okay, now the degree on top and bottom can be the same. So I could put something next to the x, and the horizontal asymptote has to be at 1, so let's make this 1 over 1, because 1 over 1 equals 1. X-intercept at 0. Okay, so when x is 0, this has to equal 0, so this plus 1 has to go away. So now we've got 0 over 2 when I plug in the x is 0. 0 over 2 is 0. The y-intercept has to equal 0. So again, when I plug in x is 0, it has to equal 0. That's the same thing. Positive when x is less than -2. It's like when really small, so like -100. So it's going to be -100 over negative. A negative over a negative is positive, so we're already good. Or x is greater than 0. So let's try like a million. So a million over, yeah, that would be positive as well. That's good. But negative, we're between -2 and 0. So let's say at -1. So this will be -1 times 1 is -1. -1 plus 2 is +1. Negative over positive. Yep, this all works. All right, the key is we have an asymptote at -2, and we have a 0 at 0. And so those are the two spots. Like that's basically those are the edges of where things could change from negative to positive or positive to negative. So if we test a value in between those two and it's negative, then we know it's negative for that whole region. All right, this graph is pretty easy to do. You know it's got a 0 right here, so it's got to go down here, and it's going to come up this way. You just kind of follow your nose. It always knows where to go. Right, I know it's got to follow this horizontal asymptote somehow, and if it's going through this 0, well, there's no way it can be coming down through this 0, because how would it ever get back up to this horizontal asymptote? So it must be going up, and that means it crosses here, which means it has to go down to this vertical asymptote. And since there's only a single, it's not order 2 here, it means it's got to come from this side, and then it's got to go back down to this horizontal asymptote without crossing 0. So it all just, like, there's nothing that could possibly happen that's different from this. And just to double check, you see how it's positive in this region, and then negative in this region, and then positive in this region. All right, let's try part C, a hole at x equals 3. So that means we're going to have a x minus 3 on both top and bottom. No vertical asymptotes. Well, of course not. That would mean that this wouldn't be able to cancel. We only want degree 1 on top and bottom. And if we have a hole, that means they have to both be the same. And so, of course, there's no vertical asymptote, because a vertical asymptote requires that this is not the same as the one on top. Y-intercept at 0, 0.5. Okay, I'm going to have to modify one of these to make it 0, 0.5. So when I plug in a 0, the top I got -3, so on the bottom I'm going to need -6. So I'm going to have to double the bottom here. There, that way when x is 3, these are still both 0, so we do have a hole. But now where does it say that? The x-intercept, if you plug in a 0, you get -3 over -6, and that's going to be 1/2. So that'll satisfy that as well. Still no vertical asymptote, so this satisfies everything. Now if you notice, if I take out the x minus 3 here, basically we just have f of x equals 1/2. The x minus 3's cancel with a hole at x equals 3. So this is not, like, there's no horizontal asymptote either. There's just the f of x equals 1/2 the whole time. Except, of course, at the hole here, 3, 1/2. All right, let's try part D. A vertical asymptote at x equals -2. So we'll start off with an x plus 2 on the bottom. All right, it says also at x equals 6. Well, that is impossible. Not if it's of the form ax plus b over cx plus d. You can't get two different vertical asymptotes if you only have something linear on the bottom. So I don't mind writing an equation that satisfies D, but it won't be of the form f of x equals ax plus b over cx plus d. That just doesn't make any sense. Horizontal asymptote at y equals 0, so that means the top has to be a smaller degree than the bottom. Positive when x is less than -2. Okay, so we just have to make sure we can plug in a big negative number and make it positive. So a big negative number out down here, it's going to be a negative times a negative. That's a positive. So we're going to need the top, when I put in a big negative number, we need this thing to be a positive as well. But remember, we're only allowed, it has to be a lower degree on the top than on the bottom, so that we approach, so that it has a horizontal asymptote at y equals 0. So either we have a negative leading coefficient, or we just have like a number, like a positive number here, 0x plus a positive number, right? So just a normal positive number, so like 1 over x plus 2, x minus 6. But we need this to be positive when we plug in a negative large number, right? So if I don't have an x here at all, then it will be positive if I have a positive number up here. All right, time will tell. We'll have to check the rest of the stuff here. All right, it says it also has to be positive when x is really large. Okay, so if I have a negative, let me try a negative leading coefficient and show you guys. Okay, there are a couple problems with this. When I plug in a negative large number or a positive large number, one of them is going to be negative, the other one's going to be positive, but we need this to not change. Second problem is, now I've created a 0, and that's of order 1, so that means that the graph is going to go from negative to positive or positive to negative wherever I put this. And up here it says it only changes from positive to negative at -2 and at 6, which is down here. So this would have to be a -2 or a 6, but then the problem is we would have a hole, and that's not what it's looking for. It wants these to be vertical asymptotes. So definitely we cannot have a binomial up here. I got to take that right out. It's got to be 0x plus something. So let's just say 1 over x plus 2, x minus 6. Let's see how that goes. Vertical asymptote at x minus 2 and x equals 6. Yep, that's true. Horizontal asymptote at y equals 0. Yep, because the degree on the top is smaller. Positive when x is between -2 and -infinity. So anything in here, let's try a really negative number. Yep, these will both be negative, so positive. Or when it's greater than 6. Yep, these will both be positive, so positive. Negative in between -2 and 6. Sure enough, anything between -2 and 6, then this one will be negative and this one will be positive. So let's get this guy graphed and see where it's increasing and decreasing. All right, so we know that it is positive in both of these regions, and it's negative in both of these regions. Let's see where that y-intercept is. Let x be 0. This is going to be 1 over -1 over 12. All right, let's see for increasing, decreasing. Right here, we're increasing all the way up to, yeah, maybe about 2. And then we're decreasing for the rest. Okay, I don't like the way the textbook does this because it says decreasing between 2 and infinity. That's not really true because at 6 it's not decreasing because it doesn't exist there. And at -2 is not increasing because it doesn't exist there. So apparently they just like to ignore that. So there we have it. That's the best I can do. It does not follow our rules here. I have 0x plus 1 on the bottom, but I do not have cx plus d on the, this is x squared minus 4x minus 12 on the bottom. So that does not follow this, but they gave us an impossible task. So we did our best with what we had. All right, without using a graphing calculator, compare the graphs of rational functions f of x and g of x. Honestly, I don't know what they mean by compare them. So I'll just graph them both and we'll talk a little bit about them. Let's start off with the, well, let's factor them both just to make it easier. All right, let's start off with the asymptotes now. So x equals 1 is an asymptote for f of x. And g of -3/2 is an asymptote for g of x. F of x has a 0 at -4/3. G of x has a 0 at 1. F of x has a horizontal asymptote at y equals 3. G of x has a horizontal asymptote at y equals 1/2. F of x has a y-intercept at -4. G of x has a y-intercept at -1/3. Just let x be 0 for those. All right, looks like we're ready to graph. This graph just kind of goes through here, and then it flips because there are no everything's order 1 here, so nothing stays on the same side when you get to an asymptote or a dot. They don't bounce back. This guy goes like this, which means it flips over to this side over here. All right, we can talk about, we're supposed to compare them, so I guess I could talk about increasing, decreasing, and negative, positive. So this one here is decreasing from -infinity all the way, basically the whole thing except where it doesn't exist at x is 1. And this guy's increasing the whole time except where it doesn't exist at -3/2. In terms of positive, negative, this guy's positive all the way to -4, and then negative until it gets to 1, and then positive for the rest. This guy's positive until it gets to -3/2, negative from -3/2 to 1, and then positive for the rest. All right, I don't know how else it wants me to compare them. I think that's a pretty good comparison. All right, let's go to question number 9. All right, this function gives the value of an investment in thousands of dollars over t years. What is the value of the investment after 2 years? Okay, just plug in a 2 here. So you got 30 plus 25, that's 55 over 2. That's 27.5. But it says that in thousands of dollars, so that's $27.5 thousand, $27,500. What is the value of the investment after 1 year? I'll just plug in t is 1, so 15 plus 25, you got 3540 over 1, so 40, so $40,000. What's the value after 6 months? Well, this is in years. See years, so you just put in a 0.5, so this is going to be 7.5, so 7.5 plus 25 is 32.5, divided by 0.5 is going to be 65, so $65,000. Dividing by 0.5 is just like multiplying by 2, by the way. All right, it says there is an asymptote on the graph of the function at t equals 0. That's true. Does this make sense? Explain why or why not. Well, let's actually graph this thing so that we have a good idea of what's going on. All right, so I factored the top of the equation just to make it easier. This is t plus 5/3. That means we have a 0 at negative 5/3. T on the bottom gives us an asymptote, like it said, at t equals 0. They're both degree 1, so we have a horizontal asymptote at 15 over 1, so 15. There's my horizontal asymptote. The rest of this graph is pretty easy to graph. It goes like this and like that, and it flips to the top because the t here is of order 1. And so that's our graph. Now let's kind of interpret it in terms of the function I of t. So it says explain why or why not this makes sense that they'd have an asymptote. It doesn't make a lot of sense. There's no way that it was worth infinite money and then it comes down. As a matter of fact, there's not a whole lot about this equation. I have a feeling they made a mistake in the equation. I have a feeling that either the top or bottom should be negative. But this investment looks like it's a lot of money, and it just gets worse and worse and worse until it gets down to $15,000. Well, it'll never actually hit 15,000, but it'll be getting closer and closer. So this guy, he's got to get rid of this investment as soon as possible if this is a real thing. It just gets worse and worse. All right, for part E, I'm just going to let you guys do that. If we choose a very small value of t, so like 0.0001, it's just going to be a really large number, obviously. Calculate the value. I don't feel like doing that. Do you think that the function is accurate at this time? Well, no, I don't think this thing is accurate at all. I wonder what the actual equation that they're trying to give us is. So no, I don't think any of it's accurate. As time passes, what will the value of the investment approach? Well, 15,000 if this is actually what they were trying to ask us. I have a feeling it's supposed to be like, I don't know what it was supposed to be on it, to tell you the truth. All right, an amount of chlorine is added to a swimming pool that contains pure water. The concentration of chlorine C in the pool at t hours is given by this, where C is measured in milligrams per liter. What happens to the concentration in the pool during the 24-hour period after the chlorine is added? All right, to get a visual, let's draw a graph. All right, I put my asymptote at t is -2. I put my 0 at t equals 0. These are both first degree. So this is t plus 2. This is leading coefficient of 1 on the bottom, leading coefficient of 2 on the top. This is t plus 2, not 2 plus t. It's the same thing, but it just looks uglier this way. So we have a horizontal asymptote at c of t equals 2. And so everything just kind of fits so that we can graph this nicely. There we go. Now we know this approach is 2, but let's see when we actually put in 24 what we get. So c of 24 is, this is going to be 26. 24 times 2, so 48 over 26. So plug in 24. You get 24 comma 1.846153, 846153, so on and repeated. So you can see it's getting pretty close to 2. So what happens to the concentration of chlorine in the pool during the first 24-hour period? It goes from 0 all the way to like 1.85, pretty close to 2. And it's never going to get above 2 even after a long time. So it's just going to kind of go up slightly from there.